So up until this point in calculus, we have really been focusing on calculus in a rectangular world, meaning calculus in a coordinate plane with xy coordinates. What this last unit is going to do is it's going to add some tools to our tool chest, and we're actually going to talk about 3 new categories of equations, 3 new types or 3 new worlds that we could live in besides the rectangular world. So the first of those 3 is parametric. So we're going to talk about what is a parametric equation, how does it function, why is it helpful, and when is it helpful. We're going to talk about polar, which is hopefully going to be partially review from previous classes, but we're going to build on that and we're going to do calculus with both parametric and polar. And then lastly, we're going to talk about vectors, which opens the door to a whole new kind of calculus. And something that's really interesting, and I think that you'll enjoy, is that both parametric equations and vectors tie pretty heavily to physics. And polar is just going to address a whole different kind of equation. So the big idea in Unit 9, we're going to be learning about 3 new categories of equations. And we're going to be learning about how do we do calculus, what does calculus look like in these 3 new worlds. So this lesson today is not really going to focus so much on the calculus, but it's going to focus on reviewing the ideas of what is a parametric equation, how does it work, what is polar, how do we graph polar coordinates, and then we'll actually start talking a little bit more in the second part of this lesson about how do we do calculus with parametric equations. So let's first just stop and talk about a parametric equation. So the idea of a parametric equation, or the best way to think about it, is to think 2D. Think 2 dimensions. For example, if we were throwing a ball into the air and we were modeling that velocity using an equation, we would be looking at those 2 types of motion independent of each other. Let's see if I can draw a picture to help this make a little bit more sense. So here's my attempt at a picture here. If we have a person that is throwing a ball, the horizontal and the vertical velocity are actually independent motion of each other. Let's think first about what's happening horizontally. So if we're thinking horizontally, that motion, if we ignore the wind, so we're going to ignore the wind. Let's say there's absolutely no wind. The horizontal velocity is going to be constant. It's going to be changing at a constant rate. The vertical velocity, however, is going to be constantly decreasing from the moment that the ball is released. And this is happening because gravity will be continuously accelerating the ball in the negative direction towards the ground. So this velocity is going to be totally different, the vertical velocity, than the horizontal velocity. So unlike in a typical xy coordinate plane where x is dependent on y, or looking at a function maybe defined differently, y is dependent on x, we are now looking at a situation where x and y are independent of each other. And what are they dependent on? They are dependent on time. So it should make sense for us to have an equation that models x with respect to its relationship to time and y with respect to its relationship to time. And that leads us into our idea of a parametric equation. So when x and y are both dependent on a different variable, that variable is called the parameter. And that type of equation, as we said, is called a parametric equation. We are still going to define a change that's occurring in the xy coordinate plane. We're still going to be graphing with parametric equations in the xy coordinate plane, but now we're going to be looking at x as a function of t and y as a function of t. And again, that t is called the parameter, which is basically just a placesaver for any given moment, right? T being time. At any moment, what's happening with x is calculated in one way, what's happening with y is calculated in another way. So let's go ahead and look at this example. We're going to use what we are given for x. X is the square root of t. We're going to use what we are given for y. Y is equal to t. And we're going to be looking over the interval from 0 to 4 and filling in this table. I'm going to go ahead and zoom in. All right, so x is defined to be the square root of t. I'm just going to rewrite that here. So if t is 0, x is 0. If t is 1, x is 1. If t is 2.25, x is 1.5. If t is 3.24, x is 1.8. If t is 4, x is 2. And then we're going to follow that same process for y, except y is just going to be exactly the same number as t. So we can fill those values into our table. And then we're going to plot our ordered pairs, our xy ordered pairs. So we used t to calculate our xy, but we're still going to be graphing in an xy coordinate plane. So why don't you go ahead and graph those points. Now, a couple things. This is a closed interval, so there shouldn't be any arrows on the ends of the graph. However, with a parametric equation, we're talking about motion with respect to time. So you should always show the direction that the curve is moving with arrows along the curve. So what I mean by that, I'm going to do this in a different color so you can see, is that you should have little arrows indicating it starts at 0, 0, and it's traveling to the right. And oftentimes with equations like these, you're going to see it turn back around, and the direction, those arrows, is really going to indicate the behavior that's happening. So what we just did was we looked at x and y as a function of t. We used t to calculate our x and our y, but I feel like a question that should be arising here is there a way to eliminate t, right? Could we use some algebraic skills to eliminate t? Well, let's think through that for a minute. We know that x is defined to be the square root of t, and y is defined to be t. So yeah, we could just substitute that in. X is going to be equal to the square root of y. Here's a now rectangular equation. We could simplify this a little more. We could square both sides and say that this is y equals x squared. But this needs to be on the domain that we're talking about. So if you look at your graph, what is x going from? X is going from 0 to 2 on the graph. So this needs to be on this domain from 0 to 2. So even if you change to rectangular coordinates, you need to make sure that you adjust your domain restriction to match the domain restriction that was originally there. So even though our original domain restriction was in terms of t, we're going to restrict our domain now in our rectangular formed function to be in terms of x. All right, let's look at a couple more examples. All right, number 1 here is defining x and y for us. X is defined to be t squared minus 5. Y is defined to be t over 2. We're going to graph that for values of t between -3 and 2. And then after we graph that, we're going to convert that into rectangular coordinates. So let's go ahead and set up a table. Why don't you pause the video, set up a table, and fill in that table. And I'm just going to use all the integers between -3 and 2. So here's my table set up. I'm going to go ahead and evaluate that and fill in those values. So here are my filled in values. Sorry, that's not perfectly straight there. And then we're going to go ahead and graph those points. So when I connect, I get these points. And notice that if I connect starting at that first x value, which corresponded to the lowest t value, the motion that this was moving was this way. Now I need to adjust the domain and find the rectangular form of the equation. So if x is equal to t squared minus 5, then and y is equal to t over 2, I could substitute that in. Actually, let's go ahead and change this to be t equals 2y, and we can substitute that in here. So x equals 4y squared minus 5. So here is my rectangular form. It's not easy for me to solve for y here, so I'm going to go ahead and just leave this in terms of x. The directions don't specify that we have to solve for y, so we're okay there. This is our rectangular equation, and what's the domain here? Our smallest x is -5, and our largest x all the way to the right is +4. So our domain is going to be from -5 to +4. All right, for this next one, I'm going to have you go ahead and grab your graphing calculator. I want you to see what it looks like to graph a parametric equation on your graphing calculator, and you're actually going to have to change the mode of your graphing calculator to do this. So grab your graphing calculator, hit mode, and then scroll down to where it says function, parametric, polar, and sequence. You're going to click on polar. And then once you hit y equals, you're going to see a very different y equals menu. You're going to see x sub 1 of t and y sub 1 of t. So each function you're going to have to type in the corresponding x part and the corresponding y part. So go ahead on the x of t line, type 1 over the square root of t, and on the y line, type t over t minus 1. And then go ahead and graph those ordered pairs. And I'm going to make a table just with a couple of values so that you can see what the table setup would look like, because you could still make a table on a problem like this. And when you graph this, you're going to see this teeny tiny little piece, and you can indicate the direction. And this is continuous, although it does look like on the graph it stops. It's a little hard to see what's going on there. And then let's go ahead and solve for this to be a rectangular equation. So eliminating the parameter. X is equal to 1 over the square root of t, which means if I reciprocate both sides, 1 over x equals the square root of t. So t is going to equal 1 over x squared, which we can substitute into our y equation. So y is going to equal 1 over x squared over 1 over x squared plus 1. We can multiply to get rid of this yucky complex fraction. You could leave it like that if you wanted to, but getting rid of the complex fractions, this would give me that y is going to be equal to 1 over 1 plus x squared, and this is true for x greater than 0. Let's look at one more parametric equation before we move into polar, and you can go ahead and pause the video and try and work through this problem on your own, and then unpause it when you're ready. So in problem number 3, our parameter is theta instead of t. We're being asked to sketch the plane curve x equals cosine theta and y equals sine of theta on the interval from 0 to 2 pi. So what I want you to think about is, how do I find a way to relate x and y in an equation together that involves sine and cosine? So here, if I just tried to solve for theta, I'm getting some weird inverse function. I don't really want that. So I want to say this problem involves some trig. Is there something triggy, getting triggy with it, is there something triggy that I can use to relate sine and cosine? So I want you to think about that for a minute. So I'm hoping that the trig identity that came to mind here is that we know that sine squared theta plus cosine squared theta equals 1. And now if we know that x is cosine of theta, then this can just become x squared. Cosine squared is x squared. If we know that, let's use a different color here, y is 3 sine of theta, then y over 3 is sine of theta. So we can put y over 3 squared here. This is still going to equal 1. So I like to put my x squared first. X squared plus y squared over 9 equals 1. Well, now we have the equation of an ellipse here, which means when we graph it, it should look a bit like an ellipse. So this has a center at, in case you have forgotten, this has a center at 0, 0, since there's no parentheses shifting it left or right. In the x direction, we're going out a length of 1. In the y direction, we're going out a length of 3. The only last thing we need to make sure we understand is the direction that it's going, and you can feel free to graph this on your calculator if you're interested in doing that. You can still use t even in the parametric setting, but it is going to go, thinking we're going from 0 to 2 pi. Ooh, that did not connect very well. Let's try again. It is going this direction, or it's going counterclockwise. And the reason I wanted to end with that one is because that nicely leads us into what is polar and how does it work, and that's the next topic in this video. So polar coordinates are really just an extension of the unit circle. It's as if we imposed the unit circle onto the xy coordinate plane, but the issue there is that it wouldn't cover all of the space. So what we do is we have circles, and you can see that on the graph. The polar graph is a whole bunch of concentric circles that represent each possible radius. So in polar, every ordered pair is actually the point r, comma, theta, where r is the radius, which is the distance out that we're going to go, the length outward we're going to travel, and theta being the angle as we rotate around the circle, just like we would with the unit circle. So every point on the xy plane is a point on the circle with some particular radius. So points in polar coordinates we just talked about can be represented as r theta. So the only things we need are a radius, length, and an angle in order to graph a polar point. Some things to note: positive versus negative in terms of r values tell you which direction you're moving from the origin, which in terms of polar is actually referred to as the pole. So it tells us, do we move forward or backward from the origin? So r being positive means we go out in the positive direction from the origin. R being negative means that we go out backwards from the origin, which again is referred to as the pole when we're talking about polar coordinates. And then positive versus negative angles, just as with all things in Algebra 2 and Trig, positive angles are telling us to go counterclockwise. Negative angles are telling us to go clockwise. So let's go ahead and plot some points here. 0, 0, being in terms of r and theta, is in the exact same place that the origin is. This is called the pole, but it has a radius of 0 and it has an angle of 0. So it's going to be right there, which means in the rectangular coordinates, this would also be 0, 0. This would just be the origin. If we look at the point 1, comma, pi, I'm going to try and do these in different colors. So here's blue. Let's go green next. What I'm doing is I'm going around to pi. Let's use a pointer. I'm starting at 0 and I'm going around to pi. So angle-wise, I'm going to be on this piece right over here, but I'm going out a length of 1. So that's going to mean I'm going out to this first concentric circle. So that would be this point right here. If I was to write this, so again, I'm going out 1 and my angle is pi. If I was going to write this as an ordered pair in rectangular coordinates, x is equal to r cosine theta, which we actually have that fact down here. So x would be equal to, in this case, 1 times cosine of pi, which means that x would be, cosine of pi is negative 1. The x value would be negative 1. Y is equal to r sine of theta. In this case, that's going to be sine of 1. No, I'm sorry. That's going to be sine of pi. So 1 times sine of pi, which is going to be 0. So in the rectangular realm, this would be the point negative 1, comma, 0. Negative pi, negative 2. So I'm starting here, and I'm going clockwise now since the angle is negative. I'm going backwards to pi, so I'm still going to be on the left-hand side of the x-axis if you think about this in rectangular terms. But once I go all the way around to here, I'm going backwards from the pole 2 because this 2 over here is negative. So I've gone around to get over here on the left-hand side, and then I'm going backwards out 2 circles. That point is going to be right here. And again, if x is equal to r cosine theta, this is negative 2 cosine of negative pi. That's going to give me 2. Y is going to be negative 2 sine of negative pi, which is 0. Why don't you go ahead and pause the video and see if you can work on D, E, and F on your own. All right, so for D, we're going to the angle 5 pi over 6, and we're going out 4. So 1, 2, 3, 4 is going to be right here. And then if I was to write that rectangularly, that would give me negative 2 root 3, comma, 2. And again, I'm just getting that from using these 2 facts down here to convert. And I didn't show the work on that one because I think we've seen the work quite a bit here. For E, we're going to 5 pi over 3, which is down in quadrant 4, and we're going out from the origin or from the pole 3 to get to that radius. If I was to convert that into a rectangular point, I would get the point 3 over 2, comma, negative 3 root 3 over 2. Again, using those same facts down below. And then the last one, F, negative 2, 7 pi over 4. So I'm going to 7 pi over 4, which is over on this, again, in the 4th quadrant. And I'm going backwards 2. So 7 pi over 4 is here, but I'm going to go away from the origin. So I'm going to go backwards from the origin. That's actually going to put me into the 2nd quadrant, which is going to be right there. If I was to write this as an ordered pair, this would end up being negative root 2, comma, root 2. So something else that's really important to notice is that each of these points could actually represent another point or an infinite number of points. And if you remember back to Algebra 2, we talked about terminal and coterminal angles. But the point that we just plotted, I want you to think about what's another way to describe this point right here. Well, it looks like it has a positive radius of 2. And that angle, instead of being 7 pi over 4, could just be 3 pi over 4. So it is possible that all of the points could be represented using different ordered pairs or different coordinates on this unit circle. And that's the idea here, is that there are an infinite number of right answers when we're plotting with polar points. There is another video that goes in more depth on how to graph polar and more information about that in the drive. So check that out in Google Classroom if you need some more support with polar. But let's build on this a little bit on these last couple examples. Okay, number 4 says, what would the graph of r equals 5 look like? Can you prove it by finding the rectangular equation using our conversion? So think about r equals 5. We are looking at the angle is not specified, but we are given the radius. So think about where r equals 5, and you could think back up to this graph. R equals 5 is everywhere along here. So it seems like r equals 5 would actually just be a circle. Let's see if we can prove that. So I'm going to put circle is what we think it's going to look like. Let's see if we can prove that. And we're thinking it's a circle with a radius of 5, obviously, since it says r equals 5. So what do we know? We know that x would be equal to 5 times cosine of theta. And we would know that y is equal to 5 times sine of theta. And then we're trying to come up with an equation that ties these two things together in a rectangular world, in a rectangular coordinate. And that is bringing me back to that idea of cosine squared plus sine squared equals 1. So x over 5 would be cosine if I square that. Then I get cosine squared plus sine squared. Y over 5 is what sine is, and we can square that. And that would be equal to 1. Sine squared plus cosine squared equals 1. And if we simplified this out, we would get x squared plus y squared equals 25, which is the equation of a circle with a radius of 5. Now, thinking similarly, if instead of the r value being constant, if theta is constant, what would that look like? So what would the graph of theta equals pi over 4, what would that look like? And can you prove that by finding the rectangular coordinates? So go ahead and pause the video and see if you can do that. All right, so I'm going to look at my graph really quickly again. Theta is pi over 4 right here, depending on if I'm going forward or backward with my radius. And that looks an awful lot like a line. So my thought is that this is probably a line that goes through the pole. So let's see if we can use one of these conversions to help us determine if that is true. So I have an angle. I don't have anything about r. So the only one of these 4 conversions that doesn't have anything about r is this tangent one. So tangent of theta is equal to y over x. And this just comes from using the unit circle to define tangent. If I drew a triangle, this is my y, this is my x, this is my r. Tangent of this angle would be opposite over adjacent. So that's where this conversion comes from. So tangent of theta is y over x. Tangent of pi over 4 is equal to 1 is equal to y over x, which means that this is just actually the equation of the line y equals x if we were to look at that in a rectangular world. All right, let's look at our last 2 examples. So for number 6, go ahead and grab your graphing calculator, pause the video if you need to. Push the mode button and go down to the polar mode. And now if you push y equals, you're going to see the y equals menu is in terms of r. So go ahead and type in r equals 4 sine of theta. And then go ahead and hit graph. and you're going to get a circle-looking shape. And let's go ahead and sketch that. It kind of looks more like an ellipse on my graph. It looks kind of like a smushed circle, but that might just be my zoom menu. Let's see what we get when we look at it analytically. But go ahead and draw a sketch down below. So there's my quick sketch of what I'm seeing. Now, and we were looking from 0 to 2 pi, so 1 rotation around. Then it says to convert it into rectangular form. So go ahead and see if you can do this without me helping you. See if you can figure out how to convert r equals 4 sine of theta into a rectangular equation. And given this graph, that might help you get started. All right, so hopefully you have had time to pause the video and try this. My first thought is, what happens if I actually multiply both sides by r? And why am I thinking this? Well, I'm thinking if there was an r right here, then this would just be y. Y is r sine theta. So why don't I just multiply both sides by r? That would give me r squared equals 4r times sine of theta. And the whole goal here was that I can now get a y in here. My goal is to change everything in this equation to be in terms of x and y. So now I've eliminated theta. I now have y. What's my problem now is that I still have this r squared, and r squared is not in terms of x and y. But what do we know about r squared? Well, we know that r squared is equal to x squared plus y squared. So I can substitute in over here x squared plus y squared. That's equal to r squared. This is going to equal 4y. And then I'm going to move everything onto the same side. Since I thought that this looked like a circle, I'm going to go ahead and see if that's the case. So I'm subtracting 4y on both sides. Now I need to complete the square. So x is fine. X is still going to just be x squared. Y, in order to complete the square, I need to add 4 on both sides. So this is going to become y minus 2 quantity squared equals 4. And this is my rectangular equation. And I was right. This is a circle with a radius of 2. Centered at 0, 2. So this is my center, and my radius is 2. Last question. Graph y equals 3 sine of 2 theta, and then sketch a graph below. Go ahead and do that on your graphing calculator. Pause the video. So we get this cool looking flower graph. That's what it's going to look like there. And then the hint here says, so we're going to put it in rectangular form. Hint, use the fact that we should know that sine of 2 theta is 2 sine theta cosine theta. So let's go ahead and write r equals 3 sine of 2 theta, and then let's go ahead and substitute in that property. All right, so now we have substituted in that property. Now I want you to think to yourself, I need to get x and y into this equation. How can I do that? And I'm hoping something that you're thinking is, man, I wish there was an r here because r sine of theta would be y, and I wish there was an r here because r cosine of theta would be x. Well, how could we get an r there? We could just multiply this entire equation by r squared. So that would give me r cubed equals 6 times r sine of theta times r cosine of theta, which now means I can just substitute in x and y. So I have officially gotten rid of my thetas. Now I need to get rid of my y's in order for this to be in rectangular form. Now, I don't know anything about r to the third, but I know something about r squared. I know that r squared is x squared plus y squared. So how could I rewrite r to the third, but so that I have r squared inside parentheses? Well, what if I just make this exponent 3 over 2? If I multiplied those exponents, I would get r to the third. So now if I simplify this, or if I substitute here, this is x squared plus y squared to the 3 over 2 equals 6xy, and we're not going to solve anything else. We're going to stop right there. So the idea when we're writing in rectangular form is we're really using any of those 4 polar and rectangular conversions to try and help us come up with a way to get rid of theta and r and to bring in x and y. So big ideas in this first section, understanding what a parametric equation is, that it is thinking sort of two-dimensionally about y and x being functions of something besides each other, being functions of a parameter or a different variable. And then how do we convert and graph, remembering that when we graph a parametric equation, we need to have arrows indicating direction. Then we talked about polar. Again, if you need a refresher on polar coordinates, check out the extra video on polar in Google Classroom. And then this polar conversion using x equals r cosine theta, y equals r sine theta, tangent of theta is y over x, and r squared equals x squared plus y squared, using those to really convert between different languages. And by languages, I mean rectangular versus polar. So hopefully this video helped you review different ideas about polar and parametric. And in the next lesson, we're really going to build on that and talk about how does calculus apply to these new types of functions. Looking forward to supporting you in class. Thanks for listening.